tire inflated.
Yeah, that's why I got it out.
All right. Those echo sounding problems that I showed you how to do and we were working on yesterday, do you have any questions about any of those? I can help you out with or answer. You want to get those done today. Like it says, echo sounding problems. Sometime by like tonight at midnight or whatever. Any questions? All right, and nothing in the chat. Okay, so pick two things up on the way in. Hopefully, one says creating bathymetric charts, and then there are two charts, one on front, one on the back, that have like different depths. Okay, so in the course, like in the chapter folder for this week, there's a PowerPoint here that says topographic maps and bathymetric charts. So if you're remote, this topographic map and bathymetric chart, that's what I'm going to be referring to during the period. And it's kind of big. It's like 105 megabytes because it has a whole bunch of good stuff in it. And then let's see, in that topographic map and bathymetric chart PowerPoint, it includes the two maps that students picked up in class. But there's also this link here that says how to make bathymetric charts with video. And that how to create bathymetric charts, this paper that says creating bathymetric charts, students who are in class pick that up. But there's also a video here. So whether you're remote or if you want to watch this again, because I'm going to demonstrate it like right now with you, this YouTube video, this link here in how to make bathymetric charts, this YouTube video takes you to, or this YouTube link takes you to a video that I made that demonstrates how to make bathymetric charts. But I want to like walk you through that so you understand like what the plan is. Okay, so that's where you can find the stuff in the chapter 3 folder. So it's really like in the chapter 3 folder, the topographic map and bathymetric chart paper, and then the let's see, how to make bathymetric charts with video. Okay, let me share this other screen with you. Okay, so any of you take geology like in the fall? So you looked at topographic maps like this. Do you recognize that with like the brown lines and stuff? Okay. Or if you took meteorology, let me take meteorology, and you did like isotherm maps and isobars, you know what I'm saying? So you draw like the lines and the loops illustrating areas of equal pressure, equal temperature. We do the same thing with maps and charts. So just to give you a sense as to what these two charts show you, the chart on the left is a topographic map for the Williamsport section. And it doesn't show, it's not centered on Williamsport because topographic maps are based upon a grid system for the country. But right here on the map, this is like the Newberry section of Williamsport, and the high school's right here. So I've zoomed in. This is the high school right here. The high school is actually shown right on the map as having like these little black boxes that illustrates the school itself. Also, Lambs is here, some of the other big buildings. But generally on this map, pink is like populated areas. And if it's green, that's where there's like, trees and forests and stuff. But the thing that's all over this map are these brown lines that are kind of like squiggly lines. And those brown squiggly lines represent areas of equal elevation or equal height. So the front hill, the road, runs up like this, and comes up to the school. And the thing is every time that road crosses one of those brown lines, it's a little bit easier to see on this one. That projector is not so great. Every time that road crosses one of the brown lines, it means you went up 20 more feet. So right here, it crosses a line here, one here, one here, one here. It's 20 feet for each of those lines. And then there's a little knoll at the top of the hill, and it's pretty flat coming into the school because there's no like brown lines that you cross. So what the brown lines on a topographic map illustrate are different levels of elevation. So here's a thing that I've made to help you understand how those lines go. All right, so this is like a hillside. And it doesn't matter if this is on land or underwater. But let me see. This is going to be really goofy because I want remote students to see this. So I'm going to be on those screens too, which is kind of goofy. Yeah, whatever. Okay, so here is this foam model, and they're really layers of foam, and I've colored them. Some are blue and some of this natural green. So it's like blue, green, blue, green, blue, green. And each of the layers is kind of like layers on a wedding cake. But each layer is the same thickness. So these illustrate different thicknesses of the Earth. And how you illustrate this curved shape as like a flat area going up to a hill, because this could be like the ocean floor and then a seamount that comes up. Make sure you pick up both those things. Like the ocean floor and a seamount that comes up, is that if you take these slices away, this slice, and then you can like take away this slice, the bottoms of those slices can be represented on a flat map. So this is the, I put that in the camera. This would be the topographic map that illustrates this pattern. And how I made that is, see, if I take this first green one off and put it on here, it lines up with the first like black line. And then if I take the next one off, this blue one, it lines up like, you know, with the next black line, and so on and so forth. So really what these maps and charts illustrate are areas where the elevation is the same. So this black line illustrates an elevation that's the same the whole way. There are some places where the lines are close together and some places where the lines are far apart. So on this chart here, there's places here where the lines are close. And when the lines are close together, that's a place where it's steep. So you can see here on this physical model, if this was like a flat area and you had to climb this hill, it's really steep here. It comes up very steep. But then on this side, it's a really gradual slope. And because it's a gradual slope going down, on the map, those turn out to be like lines that happen to be far apart. So that's a way in which the topographic maps are illustrated. Here, I'll go back to this thing. So like on the topographic map section, like down here in Newberry, like in the industrial park, you don't see many of those brown lines down here. It's all just kind of like a big open flat area. And most of the city, it's all pretty flat. There's not a whole lot of brown lines. But here where the hill is, you see there's tons of these lines and they're all packed in really close in here. That's because the hill's really steep. So that's the way that you see it on a topographic map. So topographic maps, they're used for land, and each line represents 20 feet. Some maps combine like topographic features, which is referring to land, and bathymetric features. So bathymetric is like ocean depth. So in this map, if it's green, that's fairly flat and low elevation. But then here, like in the Himalayas, like where Mount Everest is, it's a brighter brown and white color. It's much higher up. Similarly, you know, we've already talked about the mid-Atlantic ridge, but here for the Atlantic Ocean, it's very shallow here where it's white. And then there's the continental shelf that drops off, and then it's really deep here where it's blue. But then this mid-Atlantic ridge is illustrated like kind of in the brown color because it's higher up. So sometimes colors are used to illustrate different depths. Here's a section. This is a chart from, this is from NOAA, showing the Hawaiian Islands, which we've already talked about a couple different times in some different ways. And depths are indicated both in numbers, and it's really hard to see these numbers, but there's small numbers on the chart that show relative depths. That's the little dot, the like black sections are. But more importantly, it's also color coded, in that like here's the Hawaiian trough, it's deep, so it's like a darker color. And then places that are shallower end up to be lighter on the map. But we don't have that advantage of color shading things. Instead, the most common way to deal with depths is with contour lines, drawing lines on the map, just like on the topographic map, that illustrate areas of equal depth. So this example is a lake. This happens to be up in Canada, in Alberta. That doesn't really make a whole lot of difference. But there are places along the lake shore. So this is the lake shore here. The white is land, and this is the water. Where the water is really shallow, it's like this reddish orange color. and then where it's the deepest is like the dark blue. And a few things you can notice. If you go from the shore to where it's dark blue here, the colors change rapidly from red, orange, yellow, green, blue, and all these lines are really packed in really tight, almost like a blur of black in here. But if you were to leave this shore and head to that deepest place, the lines are far more spaced out. So it gets gradually deeper heading this way, but if you were to leave shore here, it gets deep really fast. So when the lines are packed in tight, it's a quick change in depth. When the lines are very spread out, it's a more gradual change. So that's the way that you can also interpret the map. Other things, on navigation charts, it's both color-coded and oftentimes there's numbers. So this chart here, this is the island of Antigua and Barbados, and down in this lower left-hand corner where that red, like this red area is, this little bit here is what's blown up on this map. And so let's say you're trying to like, let's say you're out here, we'll go like here, and you need to get to this place here, Johnson's Point. Maybe this is like your house on the shore. Now, like usually the shortest place between 2 points is a straight line, but this shows Cadres Reef, and this is actually submerged, but this dark blue is very shallow. If you were to take a boat and go like straight in this direction, you're going to go into very shallow water, maybe run up on this reef. It's a little deeper here, then get shallow, then deeper again. So if you're navigating a boat, you can't travel in this direction. We already looked at like the risks of getting into shallow water. So the smart thing here is to stay where the water is deep, travel like in this direction. And then here, it says numerous coral heads, but there's this shallow place here, and you can go in between those, head down like this, and then at the last minute, kind of cut in. So you're in the shallowest place for as little time as possible. And when you navigate in the water, you can't see under the water. Like if you're here, you can't tell how deep it is. The water is dark, and you can rely upon depth finders to help you out, but the navigational chart helps you get to where you need to be. So on this chart, these numbers here, like 12, 24, 19, 13, those are actually places where the depth has been measured. And this happens to be in feet, 12 feet, 24 feet, 19 feet, 13 feet. So you can see over here, there's like a 3, I think it's a 3, another 3, 8. So those are very, very, very shallow places. So if your boat has and it's possible your boat has like a 10-foot draft, which means there's 10 feet of water underneath the boat. You can't go places where it's shallower than 10. You'd run aground. The keel of the boat would touch a surface. You could damage the reef, or you could just straight up damage your boat, or just embarrassingly run aground. Okay, a lot of maps are far more complicated, showing an awful lot of stuff on them. And I'll show you a place where you can go to find them. I put a link in the folder for today. Here, let's do this. New share, Safari. So in the plan for the week, in for today, I put a thing that says NOAA Charts, and it's a link to the National Oceanographic and Atmospheric Administration. And it turns out that sailors used to have to buy charts, physical paper maps, and anywhere you wanted to go with your boat, you'd have to have the chart to be able to see where you need to be. But now almost everything's electronic, and NOAA offers electronic charts. So let's say that you're, and what you do is you download the chart, you put it on a USB drive, or some people's boats actually have the like, you know, an internet connection. So let's say that this is like Wildwood, New Jersey, and this is like the inlet between Delaware and New Jersey, and we're going to try to like travel up through this inlet. You can actually click on a box, and then it says available products ENC. That's a thing so you can download the chart to put it in an electronic chart plotter that you have, like just the same as like a GPS in a car. You can get electronic chart plotters for boats. But up here it says paper charts. So if you're interested in seeing a paper chart of anywhere around the United States, and it also works for inland waterways. So for instance, there's inland waterway information anywhere where it's like got a box. But we'll go here with this inlet is, I'll click on this one. When I click here, you can get different products, but I'll click PDF. And you can view it on a screen. You could save it on an iPad. So if you don't have a chart plotter on a boat, you could still take it with you. Or if you're doing research, you can find the place. So here's that inlet to the ocean. And it shows all these different numbers. And I can zoom way in to show you like how many numbers there are. But there's lots and lots and lots of those depths. A lot of places the depth is like 100 feet, 140 feet and whatnot. But then it turns out as you go up the river and it gets more and more shallow, as we go to the northern part of the Delaware, I got to zoom back in. One thing you'll see, if I go between the shores, there's this set of parallel lines that almost look like a road or like a highway. And there's this channel here that's almost exactly the same width and almost exactly the same depth all the way down through here. That is not natural. That's dredged. If you know about dredges, they're like big barges you go out and you either pump the sediment from the river bottom or they use like a big loader and scoop it out. And these channels are cut so that large ships can get up and down the river. And then these markers here, this thing, this thing, this thing, those are buoys. They're markers that are in the water. They're either red or green. And the ship's captain, or if you're in a boat, you know, it turns out if you're going this way, you keep those to your right. And if you're heading this way, you keep those red ones to your left. In this case, they're only red, but sometimes there's green ones too. And you go between the red and the green. But so sometimes you'll see on some of the charts, these are not natural features. This has been dredged to allow ships to come up and down. Whenever there's big heavy storms, sometimes a big storm will carry a lot of sediment down the river and dump a lot of that sediment here. But here's a place I want to show you things that are true about the charts. I don't know what the contour interval on this one is, but see if we can figure it out. Okay, I'm going to go right up in here. Okay, so look at this. Hold on, I'll take a screenshot. This part of the map, and I'm just going to put this in my drawing tool. Add a page. New share, open board. Okay, this is both color-coded, but it also has lines. So here's the thing I want you to look at. See how there's this, this bluish area here, and then it's a different blue here? There's a line that runs up this way, and then runs down that way. What's true about the numbers? I can make it just a little bit bigger. Hold on a second. So this area here I'm looking at. What's true about all the numbers that are inside the area as compared to the numbers that are outside the area? What are all the numbers inside the area as compared to outside? It is deeper. What depth would you say that this line then represents? 30? Why do you say 30? Yeah, isn't every number inside greater than 30? And every number outside is less than 30? True? So this line represents the place where the depth is the same. Now, what about this line here? So the next one off to the right, when you look at this one and you go down, every number to the left of that, bigger than 20, right? Every number to the right of that, smaller than 20. So this line must represent 20. This line represented 30. This line here, it's actually a little bit tricky because I don't know what the contour interval. It actually turns out on this map, they could be by 12. You have to look at the thing at the bottom corner. But you see everything on one side is like about greater than 10, but everything on one side is about 10 or less. So this is about the 10 line. You know what I mean? It could be by 12. But the thing about the lines is the lines represent areas of equal depth. The same thing here. Everything inside this line, this squiggly shape, everything inside there is less than 20, less than 19 or 20. So this is also like about 20. So everything inside is less than 20. Everything outside is greater than 20. There's a 19 because you got to kind of like use some judgment. And this might be a small channel here that's actually well known. All right, so here's what we're going to do. We'll go to Clearwater, Florida, so you can see where it is. And I'll show you how to make those lines on the map. Got to get to, so you've got a map that says Clearwater, Florida. I'm going to show you where that is in the world. Clearwater, Florida, Safari. Okay, we went out pretty far. So here's Florida, on the west coast of Florida. There's Tampa Bay. This is the Tampa Bay, and Tampa's on the inside. And there's this area that's west of Tampa. People generically call it like Clearwater St. Petersburg. So Clearwater is right here. So what you're actually looking at is an area that's just to the west of Clearwater. On your chart, on the right-hand side, you actually see this little tiny bit of land here in Largo, Florida. That's the thing that's hanging off the right-hand side, and actually has the word, it begins to start with the word clear. So what we're looking at is all the water that happens to be off the shore of Clearwater, Florida. Let me go back to the open board thing. Okay, so this is a good example of a bathymetric chart where someone has used a bathymetric technique. Like, you could use a weight on a rope, but we don't. It's really probably done with sounding, like with the transducers, like you do in the, like I showed you yesterday. So what you want to do is systematically measure different depths. Well, if this is the edge of land, there's the real land is here, and then there's some barrier islands and sandbars. And as you go offshore, it gets deeper and deeper and deeper. So we go out from, 1 foot, really 0 feet at the shore, all the way out to like 40, 50 feet. So it's like 54 feet out here. It just gets deeper and deeper gradually as you go to the west. So one thing you want to do is you got to figure out how many lines you want to put on the map. You could say, I'm going to put a line for every foot. But if you put a line for every foot of depth, you're going to end up with 54 lines by the time you get to the 54. And your map's going to be all garbaged up with like tons of lines, and it takes forever. You could also say, I'm going to put a line every 20 feet. Well, if you put a line every 20 feet, you're really only going to get like one line here and then one line like way over there, and doesn't show you much detail. You didn't put very many lines on the map. So a good rule of thumb that we'll use is to try to get about 10 lines on the map. So I know that like if you took geology and you did topographic map sections, the standard is to go every 20 feet. And that's just the standard. If you're doing something with isobars or isotherms in meteorology, there are other standards for the interval by pressure or interval by temperature. But for oceanography with a bathymetric chart, some of our charts, the difference in depth from deepest to shallowest might only be 10 feet. And we might also look at charts where the difference in depth is like 5,000 feet. So you can't always use the same difference in distance. So here's the smart thing to do. We want to get about 10 lines. So to get about 10 lines on the map, you take the deepest place and you subtract the depth for the shallowest place and divide it by 10. That'll give you some kind of an interval that's a nice interval. On this map, the deepest place is down here in the lower left corner. It's about 54 feet. And the shallowest place is actually land, so that's 0 feet. And if you divide that by 10, you get 5.4. but you're not going to do 5.4. That's not smart. We'll just go every 5, you know? If this came out to be like 8, maybe we'll go every 10 feet. So round it to something that's like a reasonable, nice value. So instead of 5.4, just round it to 5. So now here's the thing. All you want to do is put a continuous line on the map that illustrates places where the depth is 5 feet as a continuous line the whole way down the map. This one's actually very simple. Some of them we'll do is much more complicated. And it doesn't really matter where you start, but this one's kind of easy because there's a shore to the left. So up here at the top, you see there's a 5, and then there's a 6 and a 1. So 5's got to be between 6 and 1, but it's not directly in between 6 and 1. It's going to be closer to the 6. And then here there's places where there's actually 5s, so your line can actually go through the 5s. And then there's a 4, and then we got to go back this way. And just like I showed you in those examples where you notice that everything to one side was greater than a number and everything to the other side was less than a number, it's the same plan here. So when I drew this black line down through the map, everything to the right is less than 5, everything to the left is bigger than 5. And then you use some kind of judgment. So 7 and 1, 5 is between 7 and 1, but you're not going to put it halfway. You're going to, like 5 is closer to 7. And the 10's actually really easy here for a while because they're like kind of nice and straight. And then it's got to make a turn this way. That line still runs right down through the 10. Everything to the left is greater than 10. Everything to the right is less than 10. And then the 15. And then a good thing to do is to, it's obvious to someone looking at the map maybe what the values and the intervals are, but you can mark them maybe at the top, 5, 10, 15. What I mean by the intervals is a lot of these charts and maps down in one of the corner, it'll say contour interval 10 feet or contour interval 20 feet. And that tells you what the multiples of the places have to be. All right, draw the rest of them. 20, 25, 30, 35, 40, 45, 50. Kind of satisfying once you get the hang of it. You know what I mean? The smart thing I do is kind of look ahead of where I'm drawing to see where it's going to go. And you really want to keep it as smooth as you can. You don't want to make like right angle changes. Bless you. Try to keep it like nice and smooth. like when we started out, they were just a bunch of numbers. They're just numbers on boxes, which can tell you depth at different places. But once you draw those contour intervals, those contour lines, now very quickly you can visually see where things are different. So a couple things you can interpret. There are places where the seafloor drops off very quickly. And the place where it drops off quickly is anywhere where the lines are close. Like here, it's like 20 feet, 26 feet. Your lines might be pretty close in here, so that drops off really quick. But then there's places where they're further apart. But in general, you notice that the lines are pretty much straight up and down on the east side, but then as you go to the west, they start to like tilt, which means that from the east to the west, it drops off by like 40 feet at the top, but then at the south, it drops off from like 0 to 50 feet. So because these lines kind of tilt to the left, it tells you that it doesn't drop off as much at the north and drops off more at the south. So this is actually a very, very simple one because the lines are pretty close to parallel. But it gives you a sense as to how much the ocean floor drops off as you leave the shore and head to the west. I think there's a distance chart on over. No, I didn't include a distance chart on this one. Oh yeah, there is. In the bottom, from here to here, oops, this says 30 kilometers. That's about 18 miles. Let's see. That's 18.6 miles. So it's actually very impressive. The water around Florida is very shallow for a huge distance. So if you leave Clearwater, Florida, and you head this far out, that's a distance of about 20 miles. It's only 20 feet deep. That's it. It is not deep. It's very, very, very shallow. Similarly, if you head inland, there's not many places in southern Florida that are even 20 feet above sea level. So Florida is barely a state, and the land surrounding it is almost more state, you know? There are other places, though, where you head 20 miles offshore, and it's 2 miles deep. You know, not 20 feet deep, it's 2 miles deep. It gets real deep real fast. So this scale down here also gives you a sense as to really how shallow it is. And you can even see that on the, I'll go back to this other one, new share. So like how I showed you in Google Earth, all this area around Florida here, where it's this very light blue, this is all very shallow water. It doesn't get deep till you're way out here in the Gulf of Mexico. So we went, you know, a little ways offshore to about here, and still only like 20, 30 feet. All right, questions or problems about that? How much time do we have? 10 minutes. Okay, on the back of that, there's another one. So this is, it says Sydney, Australia. So we'll go there. Sydney. Sydney is where P. Sherman lives, the dentist in Finding Nemo. So now here, this is Eastern Australia. And when you leave Eastern Australia and head to the east, it gets pretty deep pretty quick. That blue area is not, that light blue area doesn't happen for much distance. So what you're looking at is approximately like this. So now I've rescaled the map, and you can see Sydney, and it's shallow for a little bit, but then it drops way off to the Pacific plate. Now it's really deep. So now you can see on this map, for about the same distance, it goes out to like, you know, about 5,000 feet of depth. So the first thing you got to do is figure out what your contour interval needs to be. You want about 10 lines on the map. So you take the deepest place, it's like 49, 41 feet. And because it includes shore, you can subtract 0, or it's just 49, 41, divided by 10, get you 494.1 feet. What do you want to make the contour interval? 500, sure. Why not? You know, it's a nice even round thing, 500 feet. So the first line, you're going to do at 500 feet. And, you know, it's good to start at like the edge of the margin of the chart, so you can find out where 500 is. And then you have one at 1,000. So what you'll notice here now is from shore to 500 feet, like you got to travel a long distance from shore to get to the 500 foot. Oh, crap. I don't have that up. I always forget to switch the screens. There we go. Sorry about that. So you got to go quite a long ways from shore to be able to get to 500 feet. But then you don't go very much further and it's 1,000 feet. You know, so on the Google Earth map, it was light blue for a pretty big distance. And then it gets really dark really quick, which indicates that it gets very steep in a very short distance. And then 1,500, it's also real close in here. And 2,000 is real close. So when you go by 500s, you can tell where from shore going out, it gradually drops off. And now they're all like packed in real close. 500, 1,000, 1,500, 2,000. And all you got to do it right is just, if you're doing the 500, everything on one side is less than 500, everything on the other side is greater than 500. When you do the 1,000, everything on one side is less than 1,000, everything on the other side is greater than 1,000. And then the 2,500. Let's see. There's a little trick down here where there's a little 2,800. And I'll tell you about what this circle means, but that's where that ends up. And then 4,000. So this one's completely different because we got to go a big distance to drop off 500 feet. And then all between the first and last red line on here, we've gone from 5,000 to 4,500 feet. Once you get to the 4,500 one, there's like, it's all flat. So this is like a flat ocean floor. And then all of a sudden it goes like up real steep and then it gets flat again. So anywhere where they're close together, it's like a steep uphill. And most of the ocean floor is this equal depth, pretty flat place. The abyssal plain, it's just a big flat boring, featureless floor, and this is almost a mile deep. 5,280 feet is a mile. So the reason why there's a circle here is you can end up with total circles because this represents 5,000. And it's true that everything on one side of the circle is greater than 5,000. Everything on the other side is less than 5,000. And a complete circle puts the 5017 inside, the 5,000 outside. There's also a peculiar place down here where you might see like, well, I got 3,000 and then 2,800 and then there's like another 3,800. So how do you deal with that? Well, this is a little place that's a C mount. It's a little thing that sticks up on the ocean floor. And those C mounts turn out to be like little circles. So here's another model, one of those models real quick. This is like this would be like a depression on the ocean floor, how those circles go. So here, if this were to be like most of the ocean floor and then there's a depression, because the depression is like, there's places of equal depth in different places. When you take that one apart, you've got these individual circles. And those individual circles, I don't know, what is here, end up to be the, well, that's the top, end up to be the individual circle. So you get an enclosed place. That's the outside circle, the next one in, the next one in, and then the closed circle happens to be representing like the bottom. And here on this, because they're very, very close together here, we expect it to be steep at that place. So put these back together. You see here, if I set it like that, it changes very, very drastically at the bottom part, but then it's not as much of a change at the top part. So all of these models are around for you to see and to use as like a guide, but for the next couple days, we'll be drawing and interpreting bathymetric charts. So you can see like different places of different depths and stuff. It's not that hard to do once you figure out how to do it, you know? And it lets you quickly see how the changes happen on the ocean floor. All right, if you're remote, if you have a printer and you can print them out to do it, that's good. Unless you can have like a drawing program so you can draw right on it, but it's a little bit tricky to be able to, you know, draw them, but at least you can see the way the lines go. Okay, let's see. Share screen, open board.